Hello and welcome to the webinar of Würth Elektronik Webinar. My name is Eleni Stark and I will moderate the webinar today. We are very pleased that you took the time to participate in our webinar. Our speaker today is our Product Marketing Manager, Stefan Menzel. He will hold today's webinar on how to select the proper capacitor for your design and also answer your questions. Before we start the webinar, I would like to point out one thing. You will be muted during the webinar today. This means that you can't ask us questions via microphone during the webinar. Nevertheless, you have the opportunity to ask us questions during the webinar at any time via the chat function. You'll find the chat function in the webinar control panel. The webinar will be about 30 minutes long. The chat questions will then be answered in a question-answer session following the webinar. There are 15 minutes in addition scheduled for this. If we are unable to answer all your questions within these 15 minutes, please email us at ices-webinar@we-online.com. We will try to answer all your questions promptly. At the end of the webinar, you will be asked to participate in a feedback survey. We would be pleased if you take the time to fill out the survey and help us to optimize our webinars. The link to the recording of today's webinar, as well as the presentation, will be sent to you in a separate email one day after the webinar. You can also watch the recording of today's webinar one day later on our website under the navigation point Webinars or on our Würth Elektronik YouTube channel. Now I'm giving directly to our speaker, Stefan Menzel, and I wish you an exciting webinar.
So welcome everybody. I'm also very pleased to welcome you to today's session. So listeners, today the topic will be how to select the proper capacitor for your design. My name is Stefan Menzel and I'm taking care for product marketing of capacitors at WE. Today I want to take the chance to take you on a travel through the capacitors, and the main topics for today will be aluminum electrolytics, aluminum polymer capacitors, film capacitors, and MLCCs. I want to introduce you some factors what you should take care of, because not each of them are pretty similar. Each category has some pros and cons and some specific things what you need to consider to have a well-running application, and maybe a few things you already know, but I guess a few things are maybe new or I can remind you to take care of. And mainly I want to talk today about aluminum electrolytic and MLCCs. Film capacitors will just be a quick topic for today, and we are very pleased if you have any questions to answer this afterwards. If we come to the capacitor types in general, for the comparison for aluminum electrolytics, film caps, and MLCCs, as you can see, like the traffic lights I added in, they are not really equal. So depending on the category you select, you get a big difference in what is possible and what you can go for. For example, if you take the aluminum electrolytics, as you can see, they are very good in case of capacitance. You can go to the far out range. Sure, if you need more, you have to go for supercaps, but anyway, you will not find the voltage range for supercaps. As you can see, for the aluminum electrolytics, or also called E-caps, nowadays it's 600 volts, 650. It's very special, so I wrote 600 for the general, what you can find within the market. You see the permissible current flow is not as high in comparison to different categories, and the maximum operating temperature range, maximum 150. Today normal is 105, 125, but you can find types up to 150. In this category, as in the middle, if you compare with film caps, you cannot go that high in capacitance, but you can go way higher in voltage. So you can go for 3 kV. They show better permissible current. But what you really need to take care of for film capacitors, they are limited in case of temperature. It's quite easy explainable because it's plastic film, and if you have a plastic film, it's organic material, and most of the organic materials don't like temperatures above 100 degrees. So if you come to a range of ambient condition above 100 centigrade Celsius, you really have to take a different category. You only should select film caps if you are below this range. Nowadays, more and more promoted, you find MLCCs as replacement for E-caps or tantalum capacitors, because they are now in the microfarad range. And it's interesting to replace a few E-caps or tantalum caps, but you really have to take care of some specific things and dependencies, what I want to take care of today and to talk about it. But as you can see, yes, they are limited in capacitance, but they're really good in case of permissible current, rated voltage, and also you find types mainly driven by the automotive industry up to 200 centigrade Celsius, because you need them and the powertrains at the EQs, and for this you really can go for high ranges. And yeah, for some special industry applications, more and more also high temperature levels are needed. Yeah, if we talk about aluminum electrolytic and polymer capacitors, they're both consisting of the same construction principle. I don't want to dive today into construction principles, but if we compare them on a simple level, the aluminum electrolytics, that's the old-fashioned way. You have a liquid electrolyte inside. As I said, you can go up to 600 volt. In comparison, yes, they are cheaper, and you have such a rule of thumb, may a few of you know, based on the Arrhenius formula, where you, by 10 degrees drop of the max temperature, the endurance stated in the data sheet, like 2000 hours at 105 degrees, you can double by 10 degrees. So if you would have a 2000 hour 105 degree type, if you run it at 95, it would be a 4000 hour type, as you can see by this small formula. Compared with aluminum polymer, it's not anymore a fluid material inside or liquid material. We have a solid polymer, organic polymer. You do not have these dry out behaviors because of this solid material, and you have a very, very low ESR. Some even say ultra low ESR. It's just a question how you want to do the marketing with this, but in comparison to aluminum electrolytics, the ESR is pretty low. This is super interesting for efficient things, and also if you want to carry high ripple current, the permissible ripple current is very high in comparison to standard E-caps, but nowadays still polymer caps are limited in case of voltage and in case of sizing because of this material inside. Manufacturing process is not 100% the same. A simple way to identify them you can find on the right hand side. You see normally at aluminum electrolytics you find a vent, but for polymer caps you normally don't have a vent because it's not needed anymore because of the solid material, and you cannot get any gassing inside the component. But if we talk about lifetime, as you can see, the calculation formula is a bit different. So it's by 20 degrees drop of the max temperature stated in the data sheet, you can calculate the expected lifetime with 10. So this would mean if you have a 2000 hour 105 degree type, if you come down to 85 degree, it would be already a 20,000 hour component. But don't stick with the formulas too young. I put this in a quick slide. If you take the rule of thumb, then you can see how the polymer caps behave when it comes to lower temperatures in comparison to E-caps. And as you can see, even the standard aluminum types, even if it's a 10,000 hour type at 105 degree, the polymer cap can be way better if it comes to a low temperature range because of the lifetime calculations that is in behind. Yeah, but what describes endurance, load life, and useful life? Here it's getting a bit tricky for the user because these names, or let's say these big words, are not standardized. So what means endurance for one manufacturer can be different for a different manufacturer. There's sadly no real standardization or norming in behind. And I only can give you the example how we run this for one of our snap-in series as an example. We have an endurance and a useful life, what we state to you. And for the endurance, for example, it would be a 2000 hours. In this case, it's an 85-degree type. The endurance test condition would be with max temperature, max rated voltage, max rated current. And the requirement would be for this endurance of 2000 hours, a maximum delta of the capacitance, or let's say capacitance change of plus minus 20%, but normally it's a direction of minus, what we have to consider. And please keep in mind, if we talk about endurance, useful life, and load life, we are not talking about a 100% defect. It's not the death of the ECAP. We are talking about a degradation process. And this is a very important thing what you should keep in mind, because as you can see, we also have a useful life statement. This is given with plus minus 40%. And this will be 4,000 hours. And it's, as I said, it's not the death, it's a worst case scenario what we have. It also could be that after 4,000 hours, maybe it's just 20 or 30%, but we have to give a certain criteria. And then it's depending how you dimensioned your application. Because if you say a capacitance drift of 10% is already critical, then you have to go for higher capacitance level, because then you will get issues with the endurance or useful life calculations. But if you say, hey, a drop of 50%, still my application can run properly, then even the useful life condition would be way longer. And depending on the ambient conditions, because normally you don't go for the max temperature range, you can enlarge the useful life by calculations, as I showed before. But what are the major factors if we talk about aging of ECAPs? The major drivers are the temperature, the ripple current, and the applied voltage. So what happens when you apply temperature? Too much temperature will result in electrolyte loss, because you get a certain dry out behavior. Also, you increase the leakage current, because the oxide degradation can happen, so the dielectric will be damaged by very high temperatures. In case of ripple current, what happens? You run a current over the ESR, and you have a certain self-heating, and this self-heating also results in the same properties as temperature, because with self-heating you get again a heating inside the component. And if it comes to voltage, if you get on a higher level as stated in the data sheet, for example, you have a 400 volt type, if you would apply 450 volt, you can damage the ECAP. You have a certain surge range, what would be 10%. So normally by the GIS standards, by Japanese industry standards, 10% is something what you can run as surge. So 440 would be okay, but if you go for higher ranges on short-term basis, or even on continuous condition, you will damage the dielectric, because the dielectric is not prepared for such a high voltage level. Because depending on the set voltage level for the ECAP, it will be different how much voltage the dielectric can resist until a drop within the dielectric happens and leakage current flow will increase, and dielectric will be damaged. Overall, these effects will result in two simple things. It's the capacitance decrease and the increase of ESR. Both can be critical, and the increase of ESR is also one reason. If you have the same voltage applied, or let's say the voltage ripple, and you get an increase of ESR, so over time, if you get a higher ESR and you still have the same ripple current, you have a higher self-heating. So over time, also the self-heating of the component can increase and accelerate the aging over time. But also for lifetime calculation, we can help you. It's not just up to you. We also can do calculations for you, because normally a manufacturer has deeper calculation formulas to dive into these lifetime assumptions. And I just listed some of the necessary parameters, what we need to know about the capacitor and about your conditions. So sure, life expectancy is a result of this, but what we need is applied voltage, rated voltage of the capacitors, and what do we have as ambient condition, the temperature, the frequency of ripple itself, and then we can do assumptions. And just a quick example, what we can do for client, if we have this, then we can run an expected lifetime calculation. But anyway, please keep in mind, in this case, it was estimated for 6 years, 24/7 running the application. But this 6 years would just mean a 20% drop of capacitance. So it does not necessarily mean the capacitor will fail. It's just describing the drop of capacitance and the change of dissipation factors and things like this. And if it comes to lifetime assumption, really get in touch with a manufacturer, because to get a better understanding what you can get out of your caps, you really should get in touch with the manufacturers. Yeah, here just a quick example. I will keep it within the presentation. You will get it afterwards. And if we consider lifetime, also you have something, let's say on the opposite side, that's often costs. And often we get asked, what is the possibility to have cost down? You have three factors to cost down E-caps. Mainly, it's the rated voltage, the endurance, and the max rated temperature to cost down or to decrease the costs for aluminum capacitors. For rated voltage, you really should take care that for the applied voltage, you should be around 70% of the rated voltage to get a well-running application. For the polymer camps, you can get closer for the continuous applied voltage. So this means if you're maybe running at 350 volt, 450 would be fine. It's not necessary to go for 500 or 600 because it will just increase your costs. But anyway, it could increase also your expected lifetime. For the endurance, it's a question to reduce on a necessary minimum what you can just do by lifetime assumptions and calculations. Because sure, if you go for 3,000 hours against 2,000, normally the 2,000 hour types, or let's say the types with less endurance, are cheaper because you use different electrolytes, you use different materials inside. And also a big factor can be the maximum temperature. So if it's not necessary to have 105 or 125 to select 85-degree types, sadly, you do not have way more factors to cost down E-caps, but it's really necessary to understand, yes, I can cost down with these factors, but on the opposite side, I also can decrease the lifetime expectancy, because these factors are also giving me buffer for the lifetime assumption and calculation. And as I said, these are the main factors if we do not considering capacitance per volume and special mounting types, because also for the costs, capacitance per volume and special mounting like 3-pin, snap-in or 4-pin is changing the costs in a strong way. If it comes to film capacitors in comparison, as I said, I will not say too many words today about film caps, but just to remind you why film capacitors are still needed and why film capacitors are still within the market. Because as you can see within the market, film capacitors mainly are THT products. You just will find a handful of SMT products, but with SMT you have the issue you cannot do the same encapsulation as you can do with THT. And encapsulation is strongly important for film caps because you have a plastic material inside or paper, and sadly paper or plastic are both hygroscopic. They can absorb moisture, and if you do not have a good encapsulation, it can be a pretty tough thing if you have high humidity as ambient condition, what can result in failures. But what our film caps are really good at, you do not have any DC bias behavior as you have it, for example, with the MLCCs. They can carry high current. So in comparison to E-caps and MLCCs, they are way better in case of current if you need a certain level of capacitance. Because for the MLCCs, yes, they can run more current, but they are too limited often in case of capacitance, or you need a lot of MLCCs to get to the same cap level. And what they're also very good at, let's say they're in between the E-caps and MLCC if it comes to long-term usage and lifetime expectancy, because if you run a film cap with good conditions, you can really get a long-term running product, because if you do not have too strong humidity and the encapsulation is fine, a film cap can run pretty fine for a very long time. Really keep in mind the temperature. The temperature, if you overstress a film cap, the base film will be damaged, and so the dielectric get damaged. So this can result in dramatic short circuits and capacitance decrease because of burn off of metallization and so on. So just to remind you about a few factors for film caps. Next topic will be the MLCCs. For the MLCCs, I want to talk about the classification quickly, because you differentiate ceramics into categories. You have class 1 ceramics and class 2 ceramics. So I guess everybody knows NP0 COG, X7R, X5R. NP0 COG would be class 1 because it's made with titanium oxide. The relative permittivity is low, so you only get to a range of nanofarad. You're not in the microfarad range, but you get a linear temperature dependency. You have minimum aging or no aging, or a low voltage, or even down to no voltage dependency. In comparison, if you need caps with microfarad range, you go for class 2. So you go for materials like barium titanate and also some tuning materials like yttrium additional to the barium titanate, like X5R or Y5V. You have a higher relative permittivity of the barium titanate, so you get to a higher capacitance range or higher capacitance range in comparison, but you get a very strong dependency in case of nonlinear temperature effects. You have aging behavior, you have high voltage dependency, and also so-called piezoelectric effects. And about these effects I want to take care of and to talk about now, because what you have to consider, as I said, for the class 2, you have a few tolerances what you have to keep in mind for class 2. Class 1 doesn't show so many tolerances. You have the delivery tolerance of the capacitance value, and that's it mainly. So a few of them, but it's not related to the NP0, have a linear temperature dependency, but it's not given for the NP0. If you need a very precise C value, you should go for class 1, like a clock, or if you need a proper and stable C value. If you go for class 2 ceramics, you should not 100% trust the datasheet value, because there are a lot of dependencies and tolerances in behind. Because yes, it is a nominal value what you find in the datasheet, but the question is, what do you really get out of the class 2 ceramics if you run them within the application? And I don't want to raise any concerns, because this is just physics what you have in behind, but we are really want to make you understand what you have to take care of, so if your application is running properly if you go for the range of microfarad MLCCs. Because let's start with the coding system, where the name's coming from for the MLCCs. Normally you have EIC and EIA coding. In this case, the EIA coding for the class 2, you can see as an example X7R. It's a capacitor you can use from -55 up to 125 degrees. But you have a possible change or allowed change of capacitance of ±15% over the temperature range, and it's not defined where at the temperature range this happens. Depending on the manufacturer, this effect can be smaller, but needs to be within this range of ±15%, that a manufacturer is allowed to call it X7R. And due to the fact that not everybody is used the same basic powder for ceramics, temperature behavior at different temperature levels can be different. So also, if it's very important to have stable values against temperature, you have to consider asking the manufacturer for curves for this particular temperature behavior. And if we talk about the DC bias behavior, I took an example out of our online tool, Wright Expert, taking two 100 microfarad types. One is a 1206 and the other one is a 1210. Both are X5R ceramics, so they're pretty similar, and they both have the same rated voltage with 6.3 volt. Only the size is different, and as you can see in the curves, the capacitance change is very, very strong against the voltage. So if we have the voltage effect, if we go to the rated voltage or very close to the rated voltage, this effect can be stronger than 50 or 60%, can be even up to 90%. But this means if you get close to the rated voltage, please consider and keep in mind that you lose a lot of capacitance, and it's not anymore the capacitance what you know out of the data sheet. And as you can see, with shrinking, this effect is getting less good or even worse. So if you shrink, and what is today a topic is integration density. So if you go for new designs, it can be problematic when you shrink something and go for smaller types. that you get worse effects just by the selection of smaller types. A second example I wanted to take care of is this one with 6 volt for 12.6, 12.10, 12.06 and 12.10 types. This was for a 6 volt applied voltage. It's a rated voltage of 10 volt. And as you can see, just by the selection of ceramic and size, so X7R against X5R, 1206 against 1210, you have a change of capacitance at 6 volt of minus 6% against minus 55%. So just by selecting the ceramic material and the size, you really change the capacitance you really get out of the design afterwards. And just to sum up these effects that you know, okay, what I really have to consider if I use, for example, a 22 micro X5R 1206, 20% delivery tolerance at 6 volt DC applied, it would be a change from 22 in worst case down to 6.8. So you can get a capacitance between roughly 14 against 7. So it's really a strong change of more than 30 or 40% what you have to consider within your application. If you would have taken an X7R as comparison, it would be way better. A bigger size X7R, you would be in between 15 in worst case and 25 in best case. So it's really a big difference just by the selection of ceramic and size. Yeah, and as I said, for the class 2 ceramics, they show strong dependencies, DC bias, aging, and microphonic effects or piezoelectric effects. And if we talk about piezoelectric effect, it's mainly driven by the ferroelectricity of the barium titanate. So if you bring any vibration or bending or vibration load on the ceramic body, you can induce voltage at the electrodes, and this can be even in a millivolt range, approximately up to 10 millivolt. So especially for analog designs or amplifier circuits or very precise measurement circuits, this can be a problem to take class 2 ceramics in these designs, because if you have vibration on the PCB or if you have any shock, it can really change your results of the measurement. And the inverse piezoelectric effect, if you have frequencies in the hearable range on the ceramic body or applied in the application, this can result in the opposite way, that the microstructure will start to conduct, and this will result in partial audible sound radiation. So this can be pretty noisy as well. It's not just the inductor that can make noise, it's also the MLCC, and this effect really at filters, at power modules and so on. You can really have strong noisy effects if you have frequencies or, let's say, yeah, not nice filter behaviors, and then you can get this strong radiation of noise. Last but not least is the cracking is a topic I just wanted to talk with you. It's a problem you easily can get because ceramic material is brittle. So if you introduce a lot of stress to the PCBs, MLCC can easily crack. This can result in open circuits and short circuits. And what is mainly the driver for cracks? Strong bending and vibration is normally the topic, especially depaneling. So if you split PCBs or cut them, really take care how much force is applied. The mechanical forces, especially also at plug-in connections and press fit zones. Even at the middle of the PCB, if you have MLCCs, they can crack if the plug-in and press fitting is not done pretty well, and if you apply too much force and bending on the PCB level. If you have unequal solder deposit amount, it can be an issue, because at cool down, you really can get so much stress at cool down that it really tears away the ceramic body. And also, especially inconsistent heating, for example, at manual soldering. So if you do prototyping, it can also happen if you have bigger sizes, let's say crack, because of this inconsistent heating what you have. If you do not heat them up, it's the same, similar on both sides. And said in a simple way, as bigger they are, as more prone they are to cracking. And as I said, for the MLCCs, please consider you have a DC bias effect. You should reduce the mechanical stress to a minimum on the PCB level to avoid the cracking, but this is also applicable for the class 1. Piezoelectric effects you have to consider, and also possible microphonic effects. Integration density is a topic. If you shrink something, especially if you go for new designs, keep in mind if you take existing circuits and shrink it, capacitance yield can change, and so this really can be problematic. So I want to say thank you for today and thanks for participating, and I will check if questions already occurred and will answer them as good as possible. Question for the piezo effect. So for class 1 or type 1 ceramics, this piezo effect is not applicable for type 1 or class 1 because they are built with titanium oxide, and titanium oxide is not ferroelectric. It's just an issue what you have with class 2 ceramics. So only for the ones based on barium titanate, it's an issue what you have to keep in mind. It's not necessarily an issue. It's really depending what a frequency range you have. We just get asked for temperature dependency models for LT spice of polymer capacitors. So what we can do and what we do in case of requests for temperature measurements, we do this on request. So if you request for polymer caps, we can measure this. So just feel free to get in touch with our sales guy or to drop a mail after the webinar session to ask us for a particular component, and then we can release a temperature measurement for you and prepare this for your LT spice simulation. But in general, we don't have this in the LT spice for all the caps. We have LT spice models and everything already. Also, we have this Red Expert tool where you can find a lot of things like ESR over frequency. So for all our aluminum-electrolytics and polymer caps, we also provide ESR over frequency range, what is a very nice tool, and these ones are based on real measurements. So we got asked in which direction we are pushing our development. Yeah, what are the borderlines we want to change? Yeah, we will introduce new products like super capacitors within this year, but for the existing product range, sure, voltage level, especially for ECAPs and endurance, high temperatures, these are the topics what we are driving. Also for the polymer capacitors to go up to voltage ranges between 200 and 400 volt. 400 volt with hybrid types is something what we see as the next step. For the ceramics, we already patented special measurement for high frequency up to 8 gigahertz. So we will also introduce new products in case of high frequency, and also soft termination is a topic what we will take care of for the near future. So I have one question according to the typical curve of the ECAP change against time. We will provide this to the particular person because it's tricky to provide this directly on the screen. So this question will get answered afterwards. Yes, there's also a question for the microphonic effects, how to suppress them. That's a good question. For suppressing the microphonic effects, the only thing what you possibly can do if you want to stay with the same cap is maybe to add in a resistor to change the impedance curve. This can possibly help to change the applied frequency, but if you do not switch or if you do not change something at the input filter, if you, for example, have this at the output filter, you have to change the input filter to maybe change something. You can add a resistor to the MLCC, or you really have to go for ECAP or film cap. You can try with different MLCCs, but if the topic is there, it's there. So it's not that easy just to get it away with a single MLCC. So considering different steps, it's, for example, as I said, the input filter, where you have to change something, or let's say you have to consider how to change the input, adding a resistor as an option, or you have to go for different cap technology, or to switch to class 1 ceramics, if it's possible, related to the capacitance, or replacing a single class 2 ceramic with a few class 1 ceramics. For further things, just give me a sec. So for a very good question for the DC bias, how to take care of the DC bias. So really what you should do in case of rated voltage. Normally you should overdose the rated voltage of a class 2 ceramic. So this means if you have, for example, 4 volt or let's say 6 volt, you shouldn't consider a 6.3 volt capacitor. Because you're too close to the rated voltage, so the drop related to the DC bias effect is very, very strong. You should consider going for 10 volt or even 16 or 25 to have a proper capacitance yield out of the MLCC. I know, sure, if you go for high cap values, you have a strong issue, because if you get in the range of 100 microfarad, you have the issue, you do not get any rated voltage of 16 or 25. But what to do then? Go back to smaller cap values like 47 or 22 and take a few of them, because then you get a higher rated voltage, and still a few of them can be cheaper than 100 micro. And it's better to take sometimes 247 micro with 10 volt instead of a 100 micro 6.3 volt, because the capacitance yield will be way, way better. And so with 2 caps, you get still way more capacitance. Yeah, also for the MLCCs, we got asked for if there's any safety margin in case of voltage related to the rated voltage. You know, as a manufacturer, we cannot say, hey, go over the borderline and everything will be fine. Yes, sure, there is a certain safety margin in case of surges, and also especially for spikes. But if you continuously go over the rated voltage, over time you can damage the dielectric, because the thickness of the ceramic layers is not made for higher continuous DC applied as stated in the data sheet. So on a really short-term basis, or it's surges, ceramics are pretty good against surges. But if it comes to a continuous or a longer load, you should take higher rated voltages, or to consider how to take care of. Also, there's a question: what is the dry-out behavior for the electrolytics? For the dry-out behavior, what does it mean? Electrolytic capacitor is not 100% sealed, so you have just a rubber sealant on the bottom side, which one is beaded with a aluminum can, and due to the fact that the rubber sealant is not 100% closing the cap, you have a certain interchange from outside to inside and from inside to outside, and this can result in dry out of electrolyte. So over time you lose electrolyte, and this loss in electrolyte will result in ESR increase, because you lose interconnectivity from cathode to pins, and you also will lose capacitance, because the electrolyte within the E-cap is the cathode itself. And so if you have less electrolyte inside the cap, the capacitance will decrease. So if you see over time that the E-cap decreases in capacitance, this is related to this so-called dry-out behavior. There's a pretty wide question. What is the failure characteristics and of different caps? So sadly for this session, maybe it would be a good webinar to go for this, because the failure characteristics can be pretty different. It's a good question. Mostly for the MLCCs, you cannot say if it's open circuit or short circuit. You can have both. By bending and cracking, both is possible. For film capacitors, mainly if you overstress them, you get open circuit conditions. So for film caps, mainly the failure mode, if you overstress them, is open circuit. And also in case of E-caps, it's mainly open circuit. What you can get for standard E-caps, for polymer caps, the chance of short circuit is higher in comparison to E-caps. So with polymer caps also, short circuit is a possible failure mode what you can have. And one question is, out of the capacitor types stated today, from my opinion, what would be the best? There is, so to say, no best choice, because the best choice is really related to your application. You really have to consider what you want to go for. If you need a certain level of capacitance and voltage, normally you would go for E-caps, because they are quite cheap, they have a good range of capacitance, and you can go for a quite well range of rated voltage. But you have to consider the aging. Film capacitors are very stable, but you don't get the range of capacitance. So in comparison to some E-caps, for some particular applications, you even cannot go for film caps. And for MLCCs can be a pretty good choice, because you can run them with a pick and place machine and everything. But they're good if you keep in mind the effects, what we talked about today, because otherwise you can really have scenarios within the application. You did your calculations with a 22 micro filter design, and then you take a 22 micro, bring it in the application, and it's just 10 or something, and the filter does not work properly because you didn't do your filter calculation with 10 micro. So you really have to consider for all of them, there is not just one single superior type. All of them are fitting depending to particular applications, and this is why we also say you're very welcome if we talk with each other and you tell what you need within your application. We can recommend you what would be the best choice depending on your ambient, depending on your scenarios in your application, or let's say your mission profile. And for today, we would close the webinar sessions. We still have a few open questions. These ones we will answer afterwards and directly drop mails to the related persons. So thank you very much for attending, and have a nice day. And we would be pleased to welcome you at the next webinar sessions of WE. Thank you very much and goodbye.